Welcome back, everyone, to another deep dive into the OEIS. You know, as number theory students, we can't resist these fascinating sequences. And today we're going to tackle A000151. It's called oriented rooted trees, and I think you'll find some pretty interesting connections here.
Yeah, these are always fun to explore, and yes, there is a lot to unpack with this one.
Definitely. So to make sure we're all starting on the same page, we'll be referencing the OEIS entry itself, obviously, and also the Wikipedia page for tree graph theory, for those of you who want some extra visuals along the way. So to kick things off, what actually distinguishes an oriented rooted tree from the regular trees we see in graph theory?
Well, it's all about adding a sense of direction. You see, in a regular tree, you just have those nodes and edges connecting them, right? But with an oriented rooted tree, you pick a special node. It's called the root. And then every edge is given a direction, pointing either towards or away from that root. Now, the OEIS entry actually points out that you can also think of this as a rooted tree with two colored non-root nodes to represent those directions. Kind of a cool way to think about it.
So it's like adding a flow to the tree starting from the root. I see how using two colors could be a visually simpler way to represent that flow, rather than drawing arrows on every single edge.
Exactly. And that's just one of the ways this concept reveals different representations of this same underlying idea.
Okay, so the sequence itself, A000151, gives us the number of distinct oriented rooted trees possible with a given number of nodes. The first few terms are 1, 2, 7, 26, 107. It seems to jump pretty quickly.
It does, and that rapid increase really highlights the combinatorial explosion happening here. With just a few nodes, the number of ways to arrange them in this oriented, rooted structure just grows enormously. It speaks to how quickly complexity can emerge in these seemingly simple systems. Like we start with something so basic and then boom, tons of possibilities.
That makes me think about all the computational challenges involved. If even small trees generate so many possibilities, imagine dealing with really large ones.
You're absolutely right. That's where understanding the growth of this sequence becomes really crucial, especially in fields like computer science where this stuff comes up all the time. Fortunately, the OEIS entry provides us with some helpful tools, like the generating function and the asymptotic formula.
Can you walk us through those a bit? I know the generating function is kind of like a mathematical blueprint for the whole sequence, but I'll admit I'm a little fuzzy on how it works.
Yeah, sure. Think of it as a way to package the entire sequence into a single function. So in this case, the generating function, a of x, satisfies a specific equation. And this equation relates its value at x to its values at powers of x. It's like a recursive definition encoded within a function.
Okay, so it captures that recursive nature of building up trees by adding more and more nodes. And what about the asymptotic formula? I remember it involves those constants c and d.
Right. The asymptotic formula gives us an approximation for the nth term. In the sequence, we call it a of n when n is very large. It tells us that a of n is approximately equal to c times d raised to the power of n, all divided by n to the power of 32. The key takeaway here is that d, the base of that exponential term, governs the overall growth rate of the sequence.
So a larger value of d means the number of possible trees explodes even faster as we add more nodes. Does that suggest there might be practical limits to how large a tree we can actually work with computationally?
That's a great question. And it leads us to some really interesting discussions about computational complexity and the limitations of algorithms, but we'll save that deeper dive for another time.
Fair enough. Let's shift gears a bit and talk about those cross-references to other sequences mentioned in the OEIS entry. I see connections to sequences for rooted trees and series-reduced planted trees. Why are these relationships important?
Well, these connections highlight the inherent structure and relationships between different types of trees. For instance, A000238 deals with rooted trees more generally, which means our oriented rooted trees are just a subset of that larger family. So by studying rooted trees, we can gain insights that might also apply to our specific case of oriented rooted trees.
And A038055, series-reduced planted trees, those sound pretty specific.
They are. Series reduced means there are no vertices with exactly two edges connected to them. And planted generally means the root only has one edge coming out of it. The connection with A000151 may be more subtle, perhaps in the methods used for counting or analyzing these structures.
I see. So these connections are like invitations to explore related areas of mathematics, looking for underlying patterns and similarity.
Exactly. The OEIS is like a map of the mathematical landscape, and these cross-references are the trails that lead us to new and unexpected discoveries.
Well, we certainly uncovered some interesting trails today. I'm already feeling inspired to delve deeper into some of these connections. This is what makes exploring the OEIS so rewarding. It's a constant journey of discovery.
It truly is. Each sequence is like a doorway to a whole new world of mathematical ideas. And speaking of doorways, we kind of touched on the idea earlier that an oriented rooted tree can be represented as a rooted tree with two colored non-root nodes. I think that representation deserves a bit more attention.
Yeah, I agree. It definitely piqued my curiosity. I understand how colors could, visually distinguish the direction of edges. But can you elaborate a little bit on how that mapping actually works?
Certainly, imagine you have a rooted tree, any rooted tree. Now you take all the nodes, except the root of course, and you color them either red or blue. Doesn't matter which color is which, as long as you stay consistent.
Okay, I've got my mental picture. A rooted tree with a bunch of red and blue nodes branching out.
Now here's the key. Let's just say, for the sake of argument, that a red node means the edge connecting it to its parent is pointing towards the root.
So if I see a red node, I picture an arrow going up from that node to its parent, eventually leading all the way back to the root.
Exactly. And a blue node would then mean the edge is pointing away from the root. So if you follow a path of blue nodes, you're moving further and further away from the root.
I see. It's like two different visual languages to describe the same structure.
Mm-hmm.
Arrows or colors. Are there situations where one might be more advantageous than the other?
That's a great point. In some cases, the two-color visualization might simplify things quite a bit. Imagine trying to draw out a really large tree with arrows on every single edge. It could get pretty messy. Using colors could make the overall structure and flow much easier to grasp, just at a glance.
That makes sense. Sometimes a different perspective can really clarify things. Speaking of perspectives, that makes me think about the asymptotic formula and what it tells us about the growth of this sequence. I'm still trying to wrap my head around the implications of that exponential growth.
It's certainly a key insight. Remember, the asymptotic formula tells us that as the number of nodes, n, increases, the number of oriented rooted trees grows roughly proportionally to d raised to the power of n. And that exponential term really dominates the formula, even though we are dividing by n to the 32 power.
So no matter how much that denominator tries to slow things down, the exponential term wins out in the end.
Precisely. It tells us that even small increases in the number of nodes can lead to a massive explosion in the number of possible trees. Think about what that means in the context of algorithms, for example.
That's what I was thinking about earlier. If an algorithm has to search through all these trees or manipulate these trees, and the number of possibilities grows so rapidly, doesn't that suggest some pretty serious limitations on what we can actually do?
Absolutely. It highlights the importance of designing really efficient algorithms, especially when we're dealing with structures that exhibit this kind of combinatorial growth. There's a whole field of computer science dedicated to analyzing these complexities and finding clever ways to manage them.
It's just incredible how a seemingly abstract mathematical concept like this can have such profound real-world implications.
That's the beauty of mathematics. It often reveals these hidden connections between seemingly disparate areas of study.
Now, before we move on, I want to kind of revisit those cross-references to other sequences. We briefly touched upon A000238 rooted trees and A038055 series-reduced planted trees. It feels like there's more to uncover there.
You're right. Those connections deserve a closer look. Remember, A000238 deals with rooted trees in a broader sense. Our oriented rooted trees are just a special case where we've added direction to the edges.
So by studying the properties and patterns of rooted trees in general, we could potentially gain insights that apply to our oriented rooted trees as well.
Exactly. It's like zooming out to see the bigger picture. And when we look at A038055, series-reduced planted trees, things get even more specific. These are rooted trees where no node has exactly two edges coming out of it, and the root itself only has one edge.
Okay, so a very particular type of tree. I'm still trying to see how that connects back to our oriented rooted trees.
The link might not be obvious at first glance, but it could lie in the methods used to analyze and enumerate these structures. It's possible that techniques developed for studying series-reduced planted trees could be adapted or applied to our oriented trees as well, maybe leading to new insights or discoveries.
I see. So exploring these related sequences isn't just about finding, direct applications, but also about broadening our understanding of the underlying mathematical principles at play.
Precisely. It's about looking for patterns, looking for connections, looking for shared structures. It's like being a mathematical detective, uncovering these hidden relationships and piecing together a deeper understanding of the world of trees. And there's one more connection we need to unravel. Remember that intriguing concept of self-convolution and its link to sequence A000551, which deals with unlabeled rooted trees.
That's the one I've been waiting for. That idea of building oriented trees from pairs of unlabeled trees really sparked my curiosity. Can we delve into that a bit further?
Absolutely. Let's unpack that. So recall that A0075 enumerates unlabeled rooted trees, meaning we don't really care about specific labels on the nodes, just the overall structure.
Right, so it's like having a blueprint for all the possible tree shapes with a given number of nodes.
Exactly. Now, this self-convolution idea, it tells us that we can take two of these unlabeled rooted trees from A000750 and combine them in a very specific way to construct an oriented rooted tree.
I remember you mentioned designating one tree as the source and the other as the destination, and then connecting their roots with an edge.
Precisely. And the direction of that connecting edge, that determines the orientation for the whole combined tree. So if the edge points from the source to the destination, then all the edges in the final tree will be oriented towards the root of that destination tree. And, reverse the edge and you'll reverse the orientation.
So it's like we're taking these two tree shapes, we're gluing them together at their roots, and then we just add a flow direction. And by considering all the possible pairings from A000575 and both flow directions, we can generate all the oriented rooted trees.
That's a great way to put it. It's this systematic way to build up more complex structures from these simpler components. The self-convolution relationship. It really reveals a deeper structural connection between these seemingly different types of trees.
It's amazing how such a simple operation can lead to such huge insights. It really highlights the elegance and just the interconnectedness of mathematics, doesn't it?
Absolutely. And, I think it reinforces the importance of understanding these really fundamental concepts like rooted trees and convolutions. These ideas provide a powerful lens through which to view these more complex structures.
Yeah, I couldn't agree more. This has been a truly enlightening journey exploring A000151, the sequence of oriented rooted trees. We've moved from these basic definitions to these complex formulas, uncovered these fascinating connections with other sequences along the way.
And through it all, we've kind of witnessed how even a seemingly simple concept like a tree can lead to such rich and unexpected mathematical explorations.
It's a great reminder that there's always more to discover, more connections to uncover, more beauty to find within this vast world of the OEIS.
Well said. It's a journey that never truly ends.
And on that note, we'll wrap up our deep dive into OEIS sequence A000151. Thank you all for joining us on this mathematical adventure.